The group 5 instruments, they are the reciprocating instruments. Instruments that neither rotate, okay, nor move up and down, but they are reciprocating instruments. Means they would have a to and fro clockwise, counterclockwise motion inside the root canal. They are the group 5 instruments. And finally, the group 6 instruments. That neither rotate. Group 6 instruments, they involve the sonic and the ultrasonic instruments. So this is a simple classification of instruments grouped into 6 categories. And what is the method? The method of use is the method that we use for the classification. You can see from group through 1 through group 6, each instrument is used in a different manner, from hand use to sonic and ultrasonic instruments. Now we'll talk about the details of these instruments. Firstly, we'll see the group 1 instruments, that are hand use instruments. And a hand instrument has a general geometry like this, which consists of 3 parts in a hand instrument: the blade of the instrument, the shank of the instrument, and the handle of the instrument. So basically, there are 3 parts into it. These group 1 hand instruments are of 2 types: the K type instrument and the H type instrument. Both these instruments, they are ISO normed, means they follow certain standard design principles as mandated by International Standardization Organization. And 2 categories of instruments are broadly used: the K type and the H type instruments. The K type instruments, the word is derived from the Kerr Manufacturing Company. This was the first company that made the standard hand K type instruments. The H type instruments, they involve the headstrong instruments. Okay. So whether it is a K-type instrument or a H-type instrument, it is a group 1 instrument that consists of 3 parts: the handle, shank, and the blade. So what are the ISO standardization for it? The ISO standardization says that the blade of the instrument is always 16 millimeter length. Okay. Length of the instrument, whether it is a K-type or a H-type instrument, any instrument, the length of the instrument consists of 2 parts. That is the shank plus blade. So principally, 3 lengths of instruments are available: 21 millimeters, 25 millimeter, and 31 millimeter. I am talking about the group 1 hand use instruments, and we are looking at the standardization parameters according to ISO. Okay, the first one is the blade length, the second one is length of the instrument, the third one, according to the ISO parameters, it is the tip angle of the instrument. I have drawn instrument over there. If we talk about the angle shown with green line, this is called tip angle of the instrument. This tip angle of the instrument is 75 degrees plus minus 15 degrees, ISO standardization. So tip angle would be 75 degrees plus minus 15 degrees. Another standardization for the instrument, okay, is the size of the instrument, its color code, and its D0. D0 of the instrument means diameter at tip of the instrument. I will again draw the diagram for this: the handle, the shank, and the blade. Okay, this instrument has the narrowest diameter, that is known as at the tip, called D0. Diameter at 1 millimeter from the tip is called D1. At 2 millimeter from the tip is called D2. 3 millimeter from the tip is called D3, and so on up to D16. So an instrument that is ISO standard hand instrument would be having diameters from D0 through D16. Okay. So what is D0? Diameter at tip of the instrument that is indicated by size of the instrument. So the size of the instrument, there are three special sizes, number 6, number 8, and number 10. 6 size instrument has a color of pink, which is the smallest endodontic hand instrument, gray, number 8, and purple, number 10 instrument. Then what does the size of the instrument indicates? The size of the instrument basically indicates the diameter at tip of the instrument, that is called D0. How do we get D0 of the particular instrument? You divide the size by 100, you get the D0 in millimeters. So what would be the D0 for a pink, that is the number 6 instrument? 0.06 millimeters. 0.08 millimeter diameter tip for number 8. 0.10 millimeter diameter tip for number 10 instrument. Then we have instrument sizes number 15, 20, 25, 30, 35, 40. Okay. These are the standard instruments starting from 15, and there's increment of 5 in each subsequent size. The colors are the white, yellow, red, blue, green, and black. These are the 6 standard colors that keep on repeating cyclically: white, yellow, red, blue, green, and black. So what would be the diameter at tip or D0 for a number 15 instrument? 0.15 millimeter. Divide the size by 100. So the size of the instrument indicates diameter at tip of the instrument, and diameter at the tip of the instrument is designated with D0. 0.20. Like this, we can calculate the D0 or diameter at the tip. The next instrument would be number 45, then number 50, 55, 60, and then number 70, 80, like this. You can see that from number 15 till number 60, there is an increment of 5 each. And subsequent to 60, there's increment of 10 each. So there is no 65 instrument, there's 60, 70, 80, 90, so on up to size 140. These are the sizes of hand instruments that are available in the market starting from number 6 through number 140. And there are 3 special instruments designated with colors pink, gray, and purple. And starting from number 15 till number 140, the instruments would be having sizes and colors as white, yellow, red, blue, green, and black. So again, size 45 would be what color? White. Subsequently, yellow, red, blue, green, and black. 6 standard colors that keep on repeating cyclically, and you can always calculate the D0 or diameter at tip of the instrument. Okay. Now, another standardization is taper of the instrument. Standard instruments are 2 degrees or represented as 2% taper. What is meant by taper of the instrument? If I again draw the diagram for the standard hand instrument, okay, these instruments are tapered. They are conical in shape. So diameter at tip of the instrument is the smallest diameter, that is D0, and it subsequently keeps on increasing the cross-sectional diameter till D16. So the instruments are tapered. And what is the standard taper for an instrument? It is 2 degrees or 2% taper. 2% taper means there is increment of size 0.02 millimeter per millimeter of length. What does it indicate? For each millimeter as we move up from tip of the instrument, this is tip of the instrument, the smallest diameter is D0, that is designated by standard size of the instrument. Now what would be diameter at 1 millimeter? D1. D1 would be D0 plus 0.02 millimeter. What would be D3? D3 would be D2 plus 0.02 millimeter. So the diameter increases by 0.02 millimeter. Okay, for each millimeter of length as we increase from tip toward the shank. Okay, so the standard instrument has a diameter of 0.02 millimeter. These are the ISO standards. Now we have got two type of instruments, the K type and the H type. They follow the same ISO standards and color coding as we have discussed above. These K type of instruments are further divided into two types. They are the K type reamers and files. So if we talk about the differences between the different type of instruments, the reamer and the file. Reamer is generally made from a triangular blank of metal. The cross section of reamer is triangular. Files are generally made from square blank of metal. They have a square cross section. And H-type instruments, they are made from round blank of metal. Blank means there's a wire, stainless steel wire or blank that has got different cross sections. It can be triangular in cross section, square shape in cross section, or it can be round in cross section. So the instrument that we get from a triangular cross section instrument blank is reamer, square blank, files, and from a round blank we get H-type instruments. Okay, a K-type reamer has a cross section of triangle, file has a cross section of square, but H-type instrument has a cross section of teardrop. It is not round in cross section. If you make a cross section of H-type instrument, what would be the shape? It would be teardrop in shape. So this is a small difference that you have to remember. H-type instruments are originally made from round blank of metal, but when it is manufactured, the manufactured instrument is a cross section that is teardrop in shape. If we talk about the cutting efficiency, instruments cutting efficiency, then the cutting efficiency of reamer is greater as compared to files. And the cutting efficiency of H-type instruments is highest amongst the hand instruments. If we talk about the fracture resistance, how a stronger instrument is, resistance of the fracture, then fracture resistance of a reamer is low, that of file is high, and that of H file is lowest fracture resistance. So I am comparing the group 1 instruments, the K type and the H type instruments with regard to their different properties. If we talk about motion of use, how a particular instrument would be used, then a reamer has a motion that is penetration, retraction, and rotation. Penetration into the root canal, okay, rotation, and then retraction from the root canal. Files, on the other hand, they have a pulling and rasping motion. This is also called linear motion. Okay, and H-type instruments, they also have a linear motion. But H-type instruments, we have to remember that they cut only on retraction. Means when we insert the H-type instrument, it would go smoothly. When we pull out from the root canal, it would cut the dentine. So these are the difference in the motion of use. If we talk about number of flutes, number of flutes. What is the meaning of flutes? Flutes means the number of twists per unit turn in the blade. Then the reamer has less number of flutes, a file has greater number of flutes, and this is the fundamental difference between K-type reamer and files. Okay, all other differences are indeed there, but if we have to make a strictest comparison between a reamer and a file, K-type reamer and file, then what we have to look for? We have to look for the parameter of number of flutes. The number of flutes is high for files, less for reamers. These are your group 1 instruments. Coming over to group 2 instruments. Two examples we have to remember for low speed engine driven instruments. Okay. They are the GG drills and piezo reamers. GG drills, the full form is Gates Glidden drills, and piezo reamers. If we look at the geometry of GG drills, they have a ledge type contra-angle shank, a large and thin shaft, and a flame shaped head. This is a flame shaped head. On the other hand, piezo reamers, they have a ledge type contra-angle shank, a thin long shaft, just like GG drills, but they have got a elongated head. This is a flame shaped head, and this is elongated head. This is elongated head. Okay. This is the principal difference between the geometry of GG drills and piezo reamers. Both are low speed engine driven instruments. Low speed means they are used in the range of 750 to 1500 revolutions per minute RPM. Both these instruments are available in 6 sizes, 1 through 6. Number 1 through 6. Both piezo reamers and GG drills. How do we identify them? There are rings engraved on the shank of the instrument. The number of rings correspond to the size of the instrument. So this is a number 2 GG drill. This is a number 3 piezo reamer. We can easily identify they are complete stainless steel instruments. No color coding is there. Okay, so how do we identify these instruments? What size of the instrument is this? By the number of rings engraved on the shank of the instrument. Number 1 GG drills have a head diameter of 0.5 millimeter. This is a head diameter or the size of number 1 GG drill. Subsequently, the diameter increases by 0.2 millimeters. So the respective diameters are 0.5, 0.7, 0.9, 1.1, 1.3, and 1.5 millimeters from number 1 to number 6 GG drills. If we talk about the piezo reamers, the number 1 piezo reamer has a head diameter of 0.7 millimeter. Subsequently, there is increment of 0.2 millimeter. So the diameters are 0.7, 0.9, 1.1, 1.3, 1.5, and 1.7 millimeter. So the size of the piezo ranges from 1.7 to 1.7 millimeter, and size of the GG drills ranges from 0.5 to 1.5 millimeters. Both are low speed engine driven group 2 instruments. Right. What are the uses? If we talk about the uses of GG drills, the first use is to remove lingual shoulder. Whenever we do anterior means incisors and canines, root canal access preparations, we find a lingual shoulder, that is the extension of dentine that causes the instrument to bend when it reaches the apex. Okay, so to prevent the instrument torsion. To prevent the instrument fracture, we have to remove the lingual shoulder. What is the lingual shoulder? If we look at, suppose this is a maxillary central incisor, it has a root canal anatomy like this when it is seen in a buccolingual cross section. This extension of dentine is called lingual shoulder. It is an anatomical phenomenon. And to have a straight line access to the apical foramen, we have to remove this lingual shoulder and straighten the root canal. This is done with the help of GG drill. So this is one use of your GG drill. The second use is coronal flaring of root canals. Coronal flaring of root canals. Okay. Coronal flaring of root canals. Whenever we do cleaning and shaping of the root canal and we have to enlarge the coronal 1/3 of the root canal, we can do that easily with the help of GG drills. But remember, only the coronal 1/3 up to middle 1/3. Never it is taken to the apical 1/3. Looking at the use of piezo, there is just one use of piezo, that is post space preparation. Whenever we have to do post and core, we have to remove a certain amount of gutta percha from the coronal and middle 1/3 of the root canal. That removal of the gutta percha from an obturated root canal is done with the help of which instrument? Piezo reamer. So only one documented use of piezo reamers is post space preparation. You can remember P for post, P for piezo, like this. These are your group 2 instruments. Coming over to group 3, which are the major category of instruments used. They are the rotary nickel titanium instruments. Rotary nickel titanium instruments. If we look at some of the important aspects of these nickel titanium instruments, it is an equiatomic alloy. It is basically an equiatomic alloy of 55% by weight of nickel and 45% by weight of titanium, nickel titanium. Equiatomic alloy means they would be having equal number of atoms of both the elements, but it is 55% nickel and 45% by weight of titanium, composition of nickel titanium. Okay. This nickel titanium, it exists in various forms. Okay. The austenite form, of nickel titanium. It is prevalent at high temperature and low stress. Austenite form. This austenite form of nickel titanium has a body-centered cubic structure. BCC, or body-centered cubic crystal structure. Then we have martensite form. Martensite form of nickel titanium. The martensite form is the form of nickel titanium that exists at low temperature and high stress. The stress is high, martensite form. Then in the transition between martensite to austenite and vice versa, we have R phase. R phase is the intermediate phase. If we have to talk about the crystal structure of martensite form, it is monoclinic. Sometimes it is also called HCP structure or hexagonal close-packed structure. But the better term to describe the crystal structure of martensite form is monoclinic form of crystal structure. R phase is the intermediate phase. Whenever the nickel titanium changes from austenite to martensite or vice versa, there is an intermediate phase that forms called R phase. Why it is called R phase? Because it has got rhombohedral crystal structure. It has got a rhombohedral crystal structure. Okay, R phase. These are the three principal forms. Another form of nickel titanium is M-wire nickel titanium. M-wire, as the name indicates, is the mixed form of nickel titanium that has components of the austenite, martensite, and the R phase. So these are the four principal phases into which endodontic instruments, rotary endodontic instruments are available. And depending upon the different phases and the design characteristics, the group 3 rotary or powered endodontic instruments made up of nickel titanium are divided into generations. Generations of nickel titanium instruments. What I have told above is the general metallurgy of nickel titanium, how the alloy functions. Okay. So generations of nickel titanium instruments. First generation, they are passive instruments. Passive instruments. Passive instruments means they are blunt type of geometry, not very sharp, and they cut only with the force of rotation inside the root canals. They do not have got sharp edges. Passive instruments, if we look at the cross section, they are sometimes depicted like this, the cross section. You can see the blade edges are blunt, and these blunt blade edges, they are called radial lens. They are called radial lens. These blunt, flat edges of the blade. No matter it has got 2 blade, 3 blade, 4 or 5, whatever is the number of blades, when we make cross section, we see that the blades are blunt. That's why they do not actively cut the dentine. They do so by scraping and rubbing motion of the rotating instrument inside the root canal. Example, if we have to talk about profile, GT files, and light speed. You can remember these three examples of rotary nickel titanium instruments that are passive cutting placed under group 1. Then we have group 2 instruments that are active cutting. An active cutting instrument would be having a cross section like this or this. You can see there are sharp edges on the blade that make them actively cutting. Whenever they rotate inside the root canal, they actively machine the dentine inside the root canals. And as the blades are sharp, there are no flat ends, so they do not have any radial lens. They are the active cutting second generation of nickel titanium instruments. Prominent examples are Pro Taper, M2, Endo Sequence, Race, like this. These are the prominent commercially available instruments which are placed under second generation because they are active cutting. Then we have third generation of nickel titanium instruments. Okay, they are instruments that have got special heat treatment. We subject the nickel titanium alloy to special heat treatment, so the properties of the alloy are enhanced. Special heat treated instruments. Okay, principally they contain the R phase of nickel titanium. What is R phase? We have already seen. Example of instruments which can be called the third generation of nickel titanium instruments are K3XF twisted file. high flex, CM. CM is the abbreviation that means controlled memory. Because of the special heat treatment given to this generation of instruments, they have got enhanced properties, better properties like more fracture resistance, more flexibility, better cutting efficiency as compared to regular nickel titanium instruments. The fourth generation of nickel titanium instruments, they have special movement. Special movement means they would not rotate inside the root canal. They have got special movement like up and down. These instruments are meant to move up and down inside the root canal and do not rotate, or they reciprocate, move to and fro. Example of an instrument that moves up and down is self-adjusting file, SAF, that is self-adjusting file. Example of instruments that reciprocate clockwise, counterclockwise, clockwise, counterclockwise. They are wave 1 and reciproc. There are n number of nickel titanium instruments available in the market. It is not possible to tell you each and every example, but what I am telling you, what is academically important for you guys, and the prominent examples of each generation of instruments. Then finally, we have fifth generation of instruments. They have eccentric motion. What is meant by eccentric motion? The center of rotation does not coincide with center of mass. Off-centered instruments there. If we have to look at the cross section of the instrument, okay, the instrument would rotate somewhere here around this axis marked with letter X. So the center of rotation does not coincide with center of mass. So these instruments have eccentric motion. This is sometimes also called swaggering motion. Okay, they move when they rotate, they have got a swaggering wave-like or snake-like motion inside the root canal. Okay. Snake-like motion in the root canal. Example of fifth generation is Pro Taper. Next, and Revo S. These are the fifth generation of nickel titanium instruments. So, what is nickel titanium alloy? What it is made up of? What are the two properties? What are the different phases of nickel titanium? And what are the generations of nickel titanium we have seen? Now we talk about group 5 instruments. I am skipping the group 4 instrument because group 4 consists of three-dimensionally adapting instrument, that is self-adjusting file, that we have already seen in the above examples. Group 4, self-adjusting file. The group 5 instruments, they are reciprocating handpieces. Okay, we all use handpieces, whether it is a micromotor handpiece or a air rotor handpiece, and we know that the rotate 360 degrees, full turn is there. Reciprocating handpieces, on the other hand, they have a to and fro motion. Three prominent examples of reciprocating handpieces are gyromatic, M4, and endo gripper. The gyromatic, M4, and the endo gripper. Gyromatic has a 90 degrees arc of reciprocation. 90 degrees means if we divide it into cross section, it would move clockwise and counterclockwise in a 90-degree arc, and usually it does at the rate of 3000 per minute. It reciprocates in 90-degree arc for 3000 per minute. This is basically a handpiece. So instead of transmitting a rotary force, it is transmitting a reciprocating force to a file that is attached to this, and it moves clockwise, counterclockwise, clockwise, counterclockwise inside the root canal. M4, on the other hand, has got a 30 degrees arc of reciprocation. Okay, if we look at the cross section, it would reciprocate in a 30 degrees arc of reciprocation. An endo gripper has a 45 degrees arc of reciprocation. So what is the technical difference? The technical difference between the three type of these reciprocating handpieces is the arc of reciprocation. All of them reciprocate, but at different angles, 90 degrees, 30 degrees, and 45 degrees for gyromatic, M4, and endo gripper respectively. Another important difference with respect to M4 and endo gripper is that these handpieces, they accept regular hand files. We have seen the group 1 instruments that consist of handle, shank, and blade. These regular hand files, they can be attached to these handpieces, whether M4 or endo gripper, and instead of rotating, they would reciprocate. So these are group 5 instruments. Coming over to group 6 instruments. Okay, they involve firstly the sonic ones. Sonic instruments, as the name indicates, sonic, they vibrate at the frequency of 2 to 3 kilohertz. Sonic frequency. It consists of two parts. Okay. One is the handpiece that transmits the sonic motion to the file attached to it. These handpieces are sometimes also called endosonic handpiece. Endosonic handpiece. Okay, so there would be something like this, to which we would attach a file that would vibrate at the sonic frequency, and this would then be placed inside the root canal. This root canal would be flooded with irrigant. What is the irrigant that we use with these sonic systems is saline or tap water. We use plain saline or tap water. This is the irrigant for them. And what are the files? Three special files are used with these sonic handpieces. They are the shaper sonic, rispy sonic, and trio or heliosonic. Shaper sonic, rispy sonic, and trio or heliosonic. Okay. These are the three type of files that are used. The shaper sonic file, it looks something like this. A thick file that has got barbs on it. It is similar to a barb brooch. A thinner file with less sharp barbs. It is rispy sonic, but is sometimes also called rat tail file. And trio or heliosonic is a twisted file with no sharp barbs on it. These are the three special files that are used with sonic systems or the sonic handpieces. If we have to talk about the example of sonic handpieces, they are MM1400 and MM1500 handpieces. Right. So they would be attached to these sonic handpieces that would vibrate at the frequency of 2 to 3 kilohertz, and they are then used inside the root canal that is flooded with irrigant that is called saline or Teflon. So when these instruments are suspended from a sonic handpiece and vibrated inside the root canal, okay, the vibration is generated from the point of attachment to the handpiece to about 1 to 1.5 millimeter short of tip. Okay, this apical one third of the instrument does not vibrate. 1 to 1.5 millimeter short of tip, the instrument vibrates whenever it is suspended in a sonic handpiece, and this is called sonic length. So if length of the file is suppose 10 millimeters, what would be the approximate sonic length? 1 to 1.5 millimeters short, that is 8 to 8.5 to 9 millimeters would be the sonic length. The length of vibration of the instrument is less than the length of the instrument, and this is called sonic length. Coming over to ultrasonics. These ultrasonic instruments, they vibrate at ultrasonic frequency that is 25 to 30 kilohertz as against 2 to 3 kilohertz for sonic. They again consist of two parts. One is the handpiece that transmits the ultrasonic vibration, and another is file. So the handpiece would be a special handpiece, and file, no special files are used. We use regular K files. What are K files? We have already seen. No special files are there. Regular K files are there. These ultrasonic handpieces are of two types: magnetostrictive and piezoelectric. From your perio lectures also you must be knowing that two type of scalar handpieces, the ultrasonic scalar handpieces are available, the magnetostrictive and the piezoelectric. If we look at the important differences between the two type of these ultrasonic handpieces, magnetostrictive, they have elliptical motion. Okay, they have what? Elliptical motion. On the other hand, piezoelectric have got linear motion. Okay, if we look at the heat generation, whenever they vibrate at ultrasonic frequency, heat is generated. It is more for the magnetostrictive and less for the piezoelectric. So if we look at the coolant requirement, it is more for the magnetostrictive and less for the piezoelectric because it generates less heat. And if we talk about the efficiency of magnetostrictive is less, that of piezoelectric handpieces is more, and they are more frequently used. So what is done? There's a handpiece that transmits the ultrasonic frequency to which a regular K file is attached. This assembly is then placed inside the root canal that we need to prepare, and the root canal is always flooded with some irrigant or the liquid, isn't it? Here with the ultrasonic systems, the irrigant is sodium hypochlorite and not tap water or saline. Okay, so there's a fundamental difference between the type of irrigant used for the sonic system and the ultrasonic system. Now, whenever this file is suspended with an ultrasonic handpiece and placed inside the fluid, it vibrates in a wave-like motion. wave-like motion. So this file, it would vibrate in a wave-like motion inside the root canal whenever it's suspended from the ultrasonic handpiece. So there would be points of maximum displacement of the file. Maximum displacement means from its resting position, the file would move to a maximum amplitude. These points of maximum displacement, they are called antinodes. So what we are seeing, suppose this is a file that is suspended from an ultrasonic handpiece and vibrated, it would vibrate in a sinusoidal wave-like motion with antinodes, points of maximum displacement, and points of minimum displacement from the resting position. These points of minimum displacement, they are called nodes. So there would be formation of nodes and antinodes whenever the file is suspended from an ultrasonic handpiece and vibrated. And at the tip of the file, the terminated free tip of the file, there is always formation of antinode. There would be maximum vibration. So there is a stark difference from the sonic. In a sonic handpiece, whenever we suspend the file, the apical 1/3 to 1.5 millimeter does not vibrate. The sonic length is short than the file length. Whenever we put a file in an ultrasonic handpiece, the tip of the file always shows the maximum displacement, that is antinodes. Now, whenever a file is subjected to ultrasonic vibration inside the closed confines like root canal, there are chances of fracture of the file, and fracture potential is maximum at nodes. The point that is not vibrating too much, minimum displacement, has got the highest fracture potential. So fracture is most likely to occur at the nodes, and tip of the file shows maximum displacement, that is antinodes. If we talk about mechanism of action, of these ultrasonic devices, the principal mechanism of actions, they are, firstly, there is increased temperature. All of you must have used ultrasonic scalers. We require certain amount of coolant because of ultrasonic vibration, the temperature increases. And we know that what irrigant we are using? We are using irrigant that is sodium hypochlorite. So due to increase in temperature, the efficiency of sodium hypochlorite is increased. It is more useful. A heated sodium hypochlorite solution more efficiently removes necrotic debris and pulpal remnants from the root canal. The second mechanism of action is shear stress. What is shear stress? There is sodium hypochlorite irrigant inside the root canal, and the file is vibrating inside the irrigant. So this file, it generates shear stress due to surface tension of liquid. Surface tension of liquid or the irrigant inside the root canal. And because of the vibration of the file inside the liquid and shear stress, it generates small circular currents. Small circular currents. Small intense circular currents are generated inside the liquid that is placed inside the root canal. These small intense circular currents, they are called eddy currents, and they increase the efficiency of cleaning with sodium hypochlorite. Okay. There is also formation of cavitation. Cavitation means bubbles are formed. That implode with. Okay. that implode with releasing energy. So these are the mechanisms through which ultrasonic systems act inside the root canals. There is increase in temperature. There is shear stress due to surface tension of the liquid, generating small, intense circular currents called eddy currents. And there is a phenomena called cavitation. There would be, due to ultrasonic vibration, during the positive and the negative phases, there would be formation of bubbles that burst. Implode means they would shrink and they would release energy, that is called cavitation. So cavitation and acoustic streaming or eddy currents and increase of temperature. These are the instruments which are principally used for endodontic treatment, starting from group 1, that is the hand instrument, till group 6, that is sonic and ultrasonic instruments. Okay, this is all about the today's session. See you again in another interesting session in your AIIMS 360-degree course. Till then, happy reading. Thank you for being connected with me. Good night, everyone. See you next time. Please take care.